Hello everyone, can you hear me? Um,
Yes, sir.
Okay, right. So let's begin. Today we are going to start the next chapter, which is on random variables. So what is a random variable? Let me just write down the definition first, and then I will explain. So it is basically a function from the sample space. Sample space is the set of all elementary elements. So it's basically a function from the sample space to the set of real numbers. To the set of real numbers. So a random variable x is a function from the sample space to the set of real numbers. So this guy here is called random variable. So for example, so when you toss a coin, you see two pictures. One is head, and the other one is tail. Okay. Now, if we assign two numbers to this, so let's say if I assign head means 1 and tail means 0. So if I assign a number, so head means 1 and tail means 0, and call this association by x. Okay. So then this x is a random variable. Okay. And as I said, that when I write, say, the event, so let's select the event that x is equal to 1, is same as the event of having a head. But the important difference is, so without the random variable, you have the sample space, which are some abstract objects which are not numbers. Okay? On the right hand side, when you define a random variable, you get something which are numbers. And why is this important? This is important because we can do mathematical calculation with numbers. We cannot do mathematical calculation which are not numbers, right? So the purpose is the purpose of random variable. So why random variable? Is that we can do algebraic operations. Algebraic operations. Algebraic operations means say addition, subtraction, multiplication, division with numbers only, right? So if I write say head plus tail, this doesn't have any meaning, right? So this doesn't make any sense. However, if I write say 1 plus 0, just 1 plus 0, this is perfectly fine. Now you might ask, why does it matter? Why do you want to introduce numbers, and why are we interested in doing algebraic operations like addition, subtraction, and so on? This will be clear in the next week's lecture. Why we need to do addition, subtraction, those kind of things in the sample space. The main point is that we need to map some numbers to the sample space, because the sample space is some abstract objects, some abstract images, and unless we assign some numbers to them, we cannot do any mathematics there. So that's the main purpose. Okay. Let's look at another trivial example again. So if you roll a dice, then you see the sample space. Actually, sample space are not actually numbers. So if you roll a die, you don't see numbers, right? You see pictures. You see pictures like this. Okay. Because you see some pictures like this, and to do some meaningful mathematics, you need to assign numbers to those pictures. And typically, what we do, we assign the numbers which are equal to the number of dots in the picture that you see. So, like this guy gets back to this number, and so on. And if you call this association y, then y is a random variable. One side note, so why is it called random variable? So let's write this down. Okay, so let me what's this? So you see that so this random variable is essentially a function, and the inputs of this function are some random elements of the sample space, right? So inputs of the function of the random variable, which is a function. Are some random elements of the sample space. Now once you have a random variable, you got the freedom of numbers and you can do anything with numbers, and therefore this opens up a totally new door to do all the mathematical calculations. So for example, so let's do another example. For example, you can answer any probabilistic questions in terms of random variables as well. So let me write this down, probability calculations. Okay. So you can do any probability calculations that you have been doing on any event, probability of any event. All of these questions can be translated into questions about random variables. So that is the first example. Suppose you have a coin, which is an unfair coin, and so write this down. Probability of any event of can be framed in terms of random variable. Okay. So let's do the first example of this kind. So example 3. Okay. Suppose you have a coin. And this is unfair coin. Probability of getting head is P, and probability of getting tail is 1 minus K. What we do, we toss this coin n times. Okay, so we toss this coin n times, and let x be the random variable. So let x be the random variable which counts the number of heads. Okay. X be the random variable which counts the total number of heads. We would like to answer 2 questions here. So we would like to ask 2 questions here. Number 1 is that find the all possible values of x. Okay, find the all possible values of x, and this is often called as the spectrum of the random variable. And the second question that you would like to ask is find the probability of x is equal to k for expression for all possible k. Before I move to answer this question, I'd like to make a remark here about the random variable itself. Um, so we are tossing the coin n times and we are counting the number of hits. Okay, now the number of hits is not a fixed number as you have realized. It could be anything random. Because if you toss a coin 10 times, you are not sure how many hits you are going to get. But what I would like to specifically mention here is that the sample space is going to be many different arrangements of head and tail. For example, it could be so like head, tail, head, right, and maybe all tails after that, or maybe tail, head, head, and all tails after that. I don't know. Like there are how many possibilities are there? There are 2 to the power n many possibilities. The sample space size is actually 2 to the power n. This is from the first lecture. So there are so many elements in the sample space, right? Maybe tail, head, so on, and not. So this random variable x, what this is doing, it is translating these sample space elements to some numbers, right? To some numbers. It's counting the number of heads. So, for example, if you look at this event, which has so let's say suppose all of these are tails, right, and so on, so all of them. So, if you look at the first two events, right, you see that the number of heads is 2 here, right? So what X is doing, it is translating these two events to the number 2, okay, and so on. So for other events, it is translating to a different number. My point was that this is not a one-to-one mapping. Okay, so this is not one-to-one mapping. This is in fact in this particular example, it's actually many to one mapping. So unlike the previous two examples that I have given you, where head is assigned to 1, tail is assigned to 0, and when you roll a die, you see the face values and you assign the number, which is equal to the number of dots. So you might be thinking, okay, so random variable is a one-to-one function from the sample space, which is not true. Random variables can be any kind of function. It can be any kind of function from the sample space. In particular, it may not be one-to-one. It may be from many elements of the sample space getting mapped with a single map, like as usual the function set. Now coming back to the answer to this question. So the first part, what are the possible values that X can take? Now if you think about this, so X belongs to, so what is X? X counts the total number of heads, right? So X counts the total number of heads. And total number of heads out of n process could be, the lowest value it could be is 0, right? So you may get like no heads, and then you may get exactly 1 head, then maybe 2 heads and so on. And the highest number of heads that you can get out of n trials is n many heads. Okay. So this is the spectrum of the random. The possible values that this X can take is from 0, 1 to 3 up here. Next part is to find the probability for all of these values. So probability of X is equal to K. So if you translate that into words, this means that you toss a coin n times. What is the probability of getting exactly K many heads? Now, if you have attended the previous lectures, I have already answered this question. So the way you do that, it's basically like there are n slots. You choose any K slots out of those n slots. You assign heads to those slots, which is 2 to the power K, because at each slot, getting a head is independent. If you toss a coin repeatedly, the trials are independent. And all other slots you get tail, which has probability 1 minus p, and there are remaining n minus k many slots. You get k. So the probability of x is equal to k is n choose k times p to the power k times 1 minus p to the power k. Most importantly, this formula is valid. This formula is not valid for all k. This formula is valid only for the k which are in this spectrum, which means this formula is valid for k is equal to 0, 1, 2, up to n. If you plug in a different value of for k, so just a star mark point. Say if I ask what is the probability, what is the probability of x is equal to say -1, which is an absurd question, like -1 number of hits, which is impossible. The probability is 0. No, that is not answered in this thing. Or if I ask like what is the probability of x is equal to 3.5, which is again an absurd question. You don't get 3.5 many hits. The answer is going to be 0. The point is that the formula that is written above is valid only for the spectrum of the random variable. Okay, for any other values, it will be 0. Does anyone have any question about this example? If you have, ask later also. Let's move to the next example. Example 4. This is kind of a continuation of the previous example. So what we do here, again we have a coin, and the success probabilities as the probability of getting hit is p. Okay. Now in this experiment, we do a little bit different style here. So we toss this coin. Actually, let me erase this. We keep tossing this coin until we get the first hit. Okay, so keep tossing this coin, until you get the first hit. Okay. What it means? It means that suppose you toss a coin. If you get a head, you stop it. You stop it there. If you get a tail, you toss it again. Okay. And if you get a tail again, you toss it again. So you keep tossing until you hit a head. Okay. Now, what is the random variable here? So let y be the random variable. Let y be the random variable. Which counts the total number of trials needed. Okay, which counts the number of trials needed. Okay. And once again, we want to ask the same questions. What are the possible values of y? What are the possible values of y? And the second question is also similar. Find probability of y is equal to k for all possible k. Once again, before going into the solution of this thing, so let's do the remark again. If you look at the sample space of this, you would see that the sample space is going to look like. So if you get a head, you stop there. But if you get a tail, you keep tossing until you get a head. Maybe like you get a head in the second time. But if you get a tail in the second time also, you keep doing. Maybe you got a head in the third time, right? So the sample space looks like this. Okay, and so on. What does Y do? So if you look at Y, what does it do? If you get a head in the first trial, the number of trials you needed to achieve that is 1. Okay, you got success in the first trial itself. But if you get a head in the second trial, then the number of trials you did is 2, right, and so on. So for the last one, for this one, you see, this is 4. Okay, the number of trials needed to achieve this is 4. So this is what Y is doing. Y is keeping track of how many times you flip the coin to get that head. Now to answer this question, so the first part, which is the possible values of Y. Now if you, as I have already explained in the picture on the left side, if you see that the possible values that Y can take, which is the number of trials needed to get the first, to get a head. The lowest number of trials needed to get a head is at least 1, right? You need to toss the coin at least once, right? Otherwise, how do you get it? And then it can keep going up. So you may get head in the second trial, or maybe you needed it for the third trial, or maybe fourth trial, right? So theoretically, it can go to infinity actually, because there is no guarantee that you would get head in 100th trial, or maybe you would get head in a millionth trial. So theoretically, there is no upper bound, which means the spectrum of Y is actually what is called the set of all natural numbers, right? Second part, probability of Y. So probability of Y is equal to K. Probability of Y is equal to K is essentially asking is that probability that the first K minus 1 trials are tails, right? So the first K minus 1 many trials are all tails, right? K minus 1 many all tails, right? And the last one is it, right? And the kth one is a head. Okay. So this is what it means by Y is equal to K. And now, how do you compute this probability? This is very simple, actually simpler than the previous one. So first K minus 1 main trials for all tails, and since these trials are independent, so this is going to be 1 minus P. So this 1 minus P is the probability of getting tail in the first trial times, because of independence, 1 minus P for the second trial of getting tail, and so on. And K minus 1th trial is also tail, which is 1 minus P. But the last trial is head, so this is P. Okay, so there K minus 1 minus P is here. Okay, so there K minus 1 minus P, and kth one is the head, which has probability. The probability is 1 minus P to the power K minus 1 times P. Once again, most importantly, whenever you're writing these probabilities, we need to write down the possible spectrum of K, which is the set of all natural numbers. Okay, so this is a very important clause here. So whenever you're writing this on a test or anything, if you're writing such probabilities, you have to mention the range of K for which this formula is valid. If you leave it blank, then this won't make any sense. Right? Why would not it make any sense? Because someone by mistake may put probability of so y is equal to as I said before, so like square root of 2. This probability cannot be obtained by 1 minus p to the power square root 2 minus 1 times p. In fact, this probability is 0 because k doesn't fall in this region of a. So it is very important you mention the range of k when you are writing this. So this is example 4. Does anyone know the last example? And so the previous two problems that we have done, I have done something which I have not pronounced. This is actually called probability mass function. Okay. Probability mass function. Or in short, this is called as PMF. Okay. So what is the probability mass function? So let x be a discrete random variable. Okay, I have not defined what a discrete random variable is. I will do so. So let x be a discrete random variable. Okay, what is a discrete random variable? Which means that x takes, or the spectrum of x, so x takes countably many values. Okay, x takes countably many values. Okay, what is countably many? Again, I will explain that. Now let the spectrum of x is the numbers, say like q1, q2, q3, so on. So for example, in the example 3, x was taking value 0, 1, 2, 3 up to n. So you can say like q1 is 0, 2, 2 is 1, 2, 3, so on. So these are the values x was taking. In the next example, it was taking 1, 2, 3, 4. You count those numbers. So suppose these are the values x is taking. Then the probability mass function of x, then the PMF of x is defined by so if x at qk is probability x is equal to qk. Okay, and this is for all qk. Okay, now I have not defined, I have not explained two important terms. One is the discrete random variable, other one is countably many values. Okay. So what is countably many things? This will be clear if I give you a counter example which is not countably many. So let's say something which is yes. Hello. So not countably many. So what is a non-countable example? Hello? Okay, so let us look at this interval. Say 1, 2, 2. Okay, and we do this experiment, which is hit at a random place in this interval 1 and 2. Okay, and x with the random variable which records the number. So x is the location. Okay, now if you think about this, how many possible numbers are there in between 1 and 2? First of all, there are infinitely many, and not only infinitely many, this is actually uncountably infinitely many. Because why is it uncountably infinite? If you think about what is counting, so whenever you count something, right, there's a concept of a starting point and the next point. Right? So if you're counting something, say, like in this example, y is taking this values, right? So start from 1, then the next value is 2, next value to that is 3, next value to that is 4, right? So you start at 1 and then you keep going next, right? In uncountable case, there is no such concept of next, right? So suppose you start at 1, right? Okay, which is good. So you start at 1, right? What is the next? What is the next to what? Is it 1.1? No, because there is a number between 1 and 1.1. So I could say like 1.01. Even no, I could again squeeze in another number like 1.001. So you see, this is never ending thing. There is no next number to 1. So you can never start the counting, right? So this is something which is uncountable. We are not talking about this scenario. We will talk about this scenario in the next lecture. So in this lecture, we are talking about the scenario where we can count, where the spectrum of the random variable is countable, where we can count like 1, 2, 3, and so on. So if that is the case, then we can write down the probability of this random variable x equal to qk, and we denote that by if substitute x qk, which is called as probability mass function. For example, the example that I have given here, like this one. So this is fy k, right? So this is PMF of y. This is probability mass function of y. In the previous example, also this was PMF of x, which was fxk. Okay. In fact, the second part of the question, which I says that find the probability x equal to k for all possible k. This can be equivalent written as find the PMF of x. Those are exactly the same questions. So in homework, if you see a problem which asks you to find the PMF or probability mass function of a random variable, it is exactly asking you to find the probability of x equal to k for all possible k. Okay, one more thing about these two problems, example 3 and 4. So in example 3, this is essentially what we say as so example 3. If you think about this, this is actually what you're doing. So here you're tossing a coin 8 times and you're counting the number of heads. Now this is just a model example. There are many similar examples. This could be like, so you roll a dice maybe 10 times and count the number of 6. Okay, or maybe many other things, right? So essentially, this is counting the number of successes in a specified number of trials, right? So this is counting. So this example 3, this model example is counting the number of successes counting the number of successes in n trials. Okay. So basically, you repeat an experiment, a specified number of times, and then you count how many number of times you get a very specific type of result, or you call it a success. Okay. So these kind of problems can be solved in exactly similar way, and this is a model example, and this model is called binomial distribution model. Okay, and we write so the random variable was x. We write that the underlying random variable follows the binomial distribution model, right? So follows sign is this tilde. Okay, so this tilde means follows the binomial model. So if I write that x follows binomial model with parameters n and p. Okay, so with parameters n and p. Once again, this tilde means follows, and these are the parameters n and p. So what is n? N is the number of trials, and p is the success probability. So my point is that the example 3 that I have given, this is actually a model problem, because this model can be applied to many similar examples. And in probability theory, this model has a very specific name also, and this name is called binomial distribution. The same goes for the example 4 as well. The example 4 that I gave here, where what you are doing, you keep tossing the coin, right? You keep tossing the coin until you get the first hit. This is again a model problem, and the same model can be applied in many different kind of problems. For example, I can ask you, keep rolling a dice until you get the point 1. Right? For some Ludo games, getting the value 1 is the starting point. Right? And then ask like how many trials you need, which is again similar to the same problem. Yeah. So this is also a model problem, and this particular model problem also has a name. And before that, let me describe what this model is. So this model, okay, so in this model, what you are doing, you are counting the number of trials needed to get the first success. So this model is for counting the number of trials to get the first success. Okay. So counting the number of trials to get the first success. And this model also has a name. This model is called a geometric distribution. And we write y follows geometric excuse me with a success probability P. Okay, so this is the success probability. Right, so someone sent me a text. All right, so basically today we talked about two model problems, which is polynomial distribution and the next one is geometric distribution. And as you can guess, in probability theory, there are many other models and each one has a name, and all of those are very well studied. So in the coming lectures this week and the next week, we will talk about many different models and different model problems. The whole idea is uh, to give you these model problems, and once a homework is assigned, you should be able to identify which model it is coming from and apply the same technique from that model. Okay. Let me see if anyone has any more question. I don't have so much time. Therefore, I would like to stop here. So if you have any question, you can ask. And you can go to this assignment tab as usual and take the survey. So if you go to the assignment tab, you will see August 31st previous date participation quiz. So you can take that quiz. And if you have any questions, you can definitely ask me. And once you are done with the session, you may leave. Once you are done with the quiz, you may leave the session.
So can we leave the class after submitting?
Yeah, so once you're done with the quiz, you may leave the class.
Sir,
Hello?
sir, in the first question, what is a random variable?
Mhm.
I have written it as a function from sample space with a set of real number, but it is showing wrong.
That's fine. I will check it. So if the computer doesn't know it, so I will check it manually.
Okay, sir.
Yeah.
Sir,
Yes.
sir, for the assignments you have given, sir,
Mhm.
one question I need to discuss that one. Sir,
Mhm.
for the question is given that what is random variable. So, sir, I submitted already my assignment.
Mhm.
So, what should we write? That I wrote that one that the quantities of maintenance that are determined by the result of the experiment are known as random variables, and we can, as it is outcomes of the experiment, so we can get the values of the experiment, so we can assign the probabilities. So but what would be the answer exactly?
If it is written in the first line of the today's lecture, right?
Okay, okay, sir. Oh, we have to write that line.
No, I mean, you don't have to write exactly the same line, but like you can write it the way you want, right? So you don't have to write the exact same line.
Okay,
I will check the answers manually. Okay.
okay, sir. Thank you, sir.
Okay, so I guess many of you have already submitted. If you don't have any question, I will close the session in 2 minutes. Okay, I'm closing the session now.